Hello everyone, so this video is going to talk about two very important word problems dealing with logs. The first one is half-life. So you'll see here the formula for half-life is A of t is equal to a sub 0 times e to the negative k t, where k is less than 0. So ultimately the k value has to be negative. So A of t is equal to the amount of the radioactive material after the amount of t years has passed. A sub 0 is the original amount of radioactive material, k is the rate of decay, and t is the time, typically in years. Now we're going to start with this particular formula, and it says strontium-90 is a radioactive material that decays according to this equation. So I'm going to just circle it here, and it says A is equal to A sub 0 e to the negative 0.0244 t. And it says, what is the half-life? So the first question here says, what is the half-life of this strontium 90? So in order to find half-life, what we have to realize is that the question is actually asking for how long is it going to take for a sample to have half of what it started with. So we're allowed to assume that we are going to start with any random amount. So let's say we started with 100 units. And now we are talking about when there are 50 units left. So it doesn't matter how much you choose to start with, but I'm going to plug in 50 into the A, and I'm going to plug in 100 into the A sub 0. And basically I'm going to times it by e to the negative 0.0244 t, and in order to solve this particular question for the half-life, I'm actually looking for the t value here. Now, if I didn't choose to start with 100, let's say I chose to start with, let's say 80, then my a value would be 40. So the cool thing about this particular formula is when I divide both sides by 100 in order to solve for the base e, I wind up with a half over here. So it's no coincidence that when you're looking for the half-life, that you wind up with a half is equal to e to the negative 0.0244 t. Now, using our rules of exponents, in order to solve this, we are going to write it logarithmically. And as we talked about earlier, remember, if it's going to be written logarithmically, it's going to be ln of a half is equal to negative 0.0244 t. And in order to solve this for t, we're going to divide by negative 0.0244. Negative 0.0244. And then in order to solve this accurately, we're going to actually type it into our calculator. Now, I've actually done this earlier, and I have this written in the calculator. So we wind up with the following. ln of a half divided by negative 0.0244. And typically we round this to 4 decimal places. So it's going to be 28.407, and then in this case 7. Now that would be years. So 28.4077 years. And what that means is it's going to take 28.4077 years in order for half of the strontium-90 to be left. So I do want to point out something that's kind of important here, and what that is the fact that if we started not with 100 units, but let's say we started with 80 units, then we are looking for when there's 40 units. When I divided both sides by 80, guess what? I'm still going to have a half. So ultimately, it doesn't matter what number you start with. When you're looking for the half-life, you wind up setting 1/2 equal to the e raised to whatever power. So that's the cool thing about half-life formulas. Now, the second part of this particular question talks about determine how long it would take for 100 grams of strontium-90 to decay to 10 grams. Now, in order to do that, we are going to use our new formula, and we are going to talk about 100 grams decaying to be 10 grams. So I'm going to set 10 equal to 100 e to the, and remember it started out as negative 0.0244, negative 0.0244t, and I'm looking for the time. So remember, using my rules of solving for exponents, I'm going to divide by 100 because I want to isolate the base, and it would be best if we divided by 100 here, and I just wrote this as 1/10. So I'm going to write it as 1/10 is equal to e to the negative 0.0244t, and then I wrote it logarithmically. So I'm going to write ln of 1/10 is equal to negative 0.0244t, and then in order to solve, I'm going to divide by negative 0.0244. Negative 0.0244, and then I'm going to type that right into my calculator. So I happen to have that over here as well. And it winds up to be T is equal to 94.36824. And remember, I would really like to see the unrounded answer first, and then we're going to round it to 4 decimal places in this case. So 94.3682 years. And that would be my final answer. So 92.43682 years. All right, let's take a look at the next question. So this next one says, what is the half-life, again, of iodine 131? And it gave me the formula. So first I'm going to do part A. So I do like to start with 100 grams. So if I started with 100 grams, I would be down to 50 grams when I was finished. So 50 is equal to 100 e to the negative 0.087t. And again, in this case, I'm looking for the t value. I'm going to divide by 100. And I wind up with 1/2 is equal to e to the negative 0.087t. And again, in this case, when I'm looking for the half-life, I'm trying to solve for the t value. Then I'm going to write it logarithmically. So it's ln of 1/2 is equal to, and it would be negative 0.087t. Then I'm going to divide by negative 0.087. Negative 0.087, and I wind up with t is equal to, and when I type that into my calculator, I wind up with this, and then when I round to 4 decimal places, I wind up with 7.9672, and in this case it was days. So you want to be super careful because in this case it was days. In the last case, in the last example, it was years. So you'll need to read your word problem carefully and make sure you have the correct unit. The second part of this word problem is specifically talking about how long does it take for 100 grams of iodine 131 to decay to 10 grams. So again, this is really literally the same setup as the first example. So we are talking about 10 grams being left, starting with 100 grams, e to the negative 0.087t. And we're trying to solve for the t value. So I'm going to divide by 100 on both sides. And I have 1/10 is equal to e to the negative 0.087t. Then I'm going to write it logarithmically. So it's going to be ln of 110 is equal to negative 0.087t. And in this case, I'm going to divide by negative 0.087, or 0.087 I should say, on both sides. And I wind up with t is equal to, in this case, 26.44649,532, and then I wind up writing t is equal to 26.465, and again this is days. So make sure you're writing days here. Okay, so that would be the second question. Now we're going to move on to the next one. So this is an interesting question because it has a lot going on here. And this is starting with what we call Newton's law of cooling. And this is kind of a new formula that you may or may not have ever seen before, so I want to make sure you understand it. And it talks about U of T. U of T, which is a temperature, is equal to T plus U sub 0 minus T times e to the negative kt. And this is kind of an important formula, and what it deals with is the following. It talks about when you take something like, for example, out of an oven. Let's say somebody makes chocolate chip cookies, and when they first come out of the oven, let's say they're cooked in a 350 degree oven. When they first come out of the oven, they're 350 degrees. And as they sit on a cooling rack, they start to lose temperature, or they start to get closer and closer to the temperature of the room. So for example, if you're making them in a oven that's 350 degrees, they start out at 350 degrees when they first come out of the oven, and as the time progresses, they get closer and closer to the room temperature. So that's what the T value is, which is the temperature of the outside or the room, and U of T is the new temperature, or as the temperature is progressing, that's what the temperature is going to be. U sub 0 is the temperature that it is like when you take it out of the oven. So it might start at 375 degrees. The room temperature might be 75 degrees. And then obviously E is the constant, or E that it's progressing down towards. And then K is the decay constant. And then T is the time. So let's take a look at an example, and I'll kind of show you how it works. So it says a pot of tea is being heated to 90 degrees. A cup of tea is poured into a mug and is taken outside where the temperature is 18 degrees Celsius. By the way, this is all Celsius. After 2 minutes, the temperature of the cup of tea is approximately 65 degrees Celsius. So the first thing it says is determine the value of the decay constant K. So what we're looking at here is the following. It says a pot of tea is heated to 90 degrees. So when it's heated to 90 degrees, that is actually going to be the U sub 0 temperature. So that 90 degrees is going to go into this spot right here. Where it says the outside temperature is 18 degrees, that's going to go into the T spot. So let me start putting some stuff in. So it's going to be 18 plus 90 minus 18 e to the negative k. We don't know what the k value is, by the way. That's what we're looking for. And then it says after 2 minutes, the cup of tea is 65 degrees. So I'm going to put the 2 minutes in here, and the temperature is 65 degrees. So that's where I would put all these numbers. So the temperature of the tea is 65 degrees. That goes in the U sub T spot. The 18 is the temperature of the room, if you will. 18 degrees, that's the T spot. So that would go in here. And then the U sub 0 is the 90. So that kind of needs to go into this spot. And then the lowercase t, in this case, the lowercase t is the 2 minutes. So this is kind of an involved formula to make sure you understand what's happening here. Now, in order for us to solve for this k value, it's important that we isolate the exponent. And in order for us to do that, obviously, we're going to get rid of this 18. So I'm going to get rid of the 18 first. 65 minus 18. By the way, let me move this word problem out of the way for a second. 65 minus 18 is going to give me 47, is equal to, and 90 minus 18 is going to be 72, e to the negative 2k. Hopefully everybody's okay with that quick math, if you will. And then I'm going to divide by 72. And then I have 47 over 72 is equal to e to the negative 2k. In order to solve this for the exponent, I'm going to write it logarithmically. So it's going to be ln of 47 over 72 is equal to negative 2k. And then I'm going to divide by negative 2. So it winds up that k is actually equal to, in this case, ln of 47 over 72 divided by negative 2, which here we have k is equal to 0.213, and I'm going to make it 3 in this case. So remember, we are rounding to 4 decimal places. So 0.2133, and that's my k value. Remember, the original question asked us to determine the value of k, or the constant, and that's going to be this 0.2133 number. Now, the next part of this question, I'm going to kind of push it up a little bit. It says, write a function of the temperature of the tea in the mug, U, in degrees Celsius as a function of time in minutes. So we kind of want to go back to this original formula. So it's going to be U of t is going to be equal to, and remember the capital T was 18 plus, and the 90 minus 18 was 72, and then it was e to the, and it's going to be negative 0.2133, and then lowercase t. So the negative itself is built into the formula. You want to make sure that we have that in the formula. The lowercase t is the time, and the u of t is the temperature that it's going to spit out. Now, you're welcome to leave this part as 90 minus 18 if you wanted to, but you can also just simplify it to be 72. Then it specifically says, using the equation you found in part B, what will the temperature in the tea be after 5 minutes? So all we're going to do is evaluate it at 5 minutes. So it's going to be 18 plus 72e to the negative 0.2133 times 5. And this is great because all you have to do is actually evaluate this particular expression in the calculator. So I'm going to kind of come back up here, pull this down, and all I did was type it into the calculator. 18 plus 72, and I wound up with 42.7832, and that would be degrees Celsius. Okay, so there's my answer, 42.7832 degrees Celsius. All right, let's move on. Now this next one is dealing with the same exact formula, which is Newton's law of cooling, and it says if the temperature of the object is 80 degrees after 5 minutes, by the way, an object is heated to 100 degrees and then is allowed to cool in a room where the air temperature is 30 degrees. So there's a lot going on with this particular question, and the way that it's different is that it does not give us the K value. So it's really important that we find the K value before we do anything. So what I want to point out is to all of you is that In this example, it's important that we use the given information to write an equation that allows us to solve for the variable k before we approach anything. So I'm going to write the formula, and it's going to be the new temperature, if the temperature of the object is 80 degrees, and by the way, it started at 30 degrees, that was the outside room temperature, and it was heated up to 100 degrees after 5 minutes. And again, we don't know the k value, so our first job is to figure out the k value. So notice my formula is 80 is equal to 30 plus 100 minus 30 e to the negative k5. And then we're going to use this to figure out the k value first. So first I'm going to minus the 30 from both sides. And then it's going to be equal to 70e to the negative 5k. And then I'm going to divide by 70. And then I have 50 over 70 is equal to e to the negative 5k. And then I want to write this logarithmically. So it's going to be ln of 50 over 70 is equal to negative 5k. And then I'm going to divide by negative 5 just to solve for k. And my k value is going to be over here. So my k value, and then when rounded to the nearest 4 decimal places, is going to be 0.0673 in this case. Now, I still technically haven't answered part A. I just did all that work just to get the k value. So I'm still in part A. I'm going to come over here and I'm going to write the equation, which is technically going to be u of t is going to be equal to 30 plus 70 e to the negative 0.0673 and then t. And then this part of the question for part A says, when will the temperature be 50 degrees? I'm going to put 50 in here. 30 plus 70 e to the negative 0.0673 t. So remember, I'm still trying to solve for the time at which the temperature is going to be 50. So I'm going to minus 30 from both sides. Then I'm going to divide by 70. And then I'm going to write this as 20 over 70 is equal to e to the negative 0.0673 t. Then I'm going to write it logarithmically. And then I think you all know how to solve this for t. I'm going to divide this by 0.0673, the negative version, of course. And as you already know, I have this in the calculator. And here's my answer. ln of 20 over 70 divided by negative 0.0673. And the t, or the amount of time it's going to take, is 18.6146. And then I have to kind of go back to the word problem to figure out if it's days or weeks or years, or in this case, guess what it is? It's actually minutes. So I know that was a long question, and that was all part A. So first I found the K value, and then I was able to go back and find the amount of time it took for the temperature to become 50 degrees. Now let's go back and figure out part B. So then it says specifically, determine the amount of time elapsed in order for it to become 35 degrees. So think about this for a second. We are going to use the same formula basically, but we are going to write 35 is equal to 30 plus 70 e to the 0.0673, and it's negative by the way, t, and then I'm going to solve this. So the first thing that I do, let me get rid of this for a second, and I'm going to erase this, it's in my way. I'm going to minus 30 from both sides, so I wind up with 5 is equal to 70 e to the negative 0.0673 t. Then I'm going to divide by 70. And then I'm going to do ln of 5 over 70 equals negative 0.0673 t, divide by negative 0.0673. And t is equal to, in this case here, so t is equal to 39.2133 minutes. And then that's that part. And then the last part, part C, what I would do, it says, what do you notice about U of t as the temperature as T increases? So what are you noticing as the temperature is increasing? It's getting closer and closer, gets closer and closer to 30 degrees. Because ultimately it's taking on the room temperature. So that's the important part of this. So keep in mind that if we were to make, like I said earlier, chocolate chip cookies, and we took them out of the oven, and they were really hot when they came out of the oven, ultimately, if you let them cool on the counter, and an hour later, they are literally going to be the temperature of the room. They are no longer going to be the temperature of the oven. And that's exactly what's happening here. So keep in mind that if you were to put something in the oven, and let's say it went to 100 degrees, and then it was to cool in a room, that the air temperature is 30 degrees, basically, even though it was in the oven at 100 degrees, it's going to level off and wind up to be 30 degrees eventually. All right, I think we have 2 more questions here. Okay, so for these last 2 questions, I'm literally running out of time, but I wrote out what you need to do in order to solve for K for this first part. So I used this information in the first line to solve for K. Hopefully you understand where that came from. And then I'm going to talk about how you can do parts A and B. So I've shown how you can solve for T equals 17.5875 minutes. Which technically the correct answer is you can eat at 5:18 p.m. And I'm going to show you how to do the last part. Because remember, the question asked for what time can you eat? And this is part B. It says determine the time that needs to elapse before the pizza is 160 degrees. So I set 160 equal to the equation to solve for t. Thanks, everybody.